Section 2 of Climatic Changes, Nature and Causes by Ellsworth Huntington. This is a LibriVox recording. All LibriVox recordings in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Leon Harvey. Chapter 2. The Variability of Climate. The variability of the Earth's climate is almost as extraordinary as its uniformity. This variability is made up partially of a long, slow tendency in one direction and partially of innumerable cycles of every conceivable duration from days or even hours up to millions of years. Perhaps the easiest way to grasp the full complexity of the matter is to put the chief types of climatic sequence in the form of a table. Table 2 is displayed on the page. Types of climatic sequence. 1. Cosmic uniformity. 2. Secular progression. 3. Geologic oscillations. 4. Glacial fluctuations. 5. Orbital precessions. 6. Historical pulsations. 7. Bruckner periods. 8. Sunspot cycles. 9. Seasonal alterations. 10. Pleiadian migrations. 11. Cyclonic vacillations. 12. Daily vibrations. In assigning names to the various types, an attempt has been made to indicate something of the nature of the sequence so far as duration, periodicity, and general tendencies are concerned. Not even the rich English language of the 20th century, however, furnishes words with enough shades of meaning to express all that is desired. Moreover, except in degree, there is no sharp distinction between some of the related types, such as glacial fluctuations and historic pulsations. Yet taken as a whole, the table brings out the great contrast between two absolutely diverse extremes. At one end lies well-nigh eternal uniformity, or an extremely slow progress in one direction throughout countless ages. At the other, rapid and regular vibrations from day to day, or else irregular and seemingly unsystematic vacillations due to cyclonic storms, both of which types are repeated millions of times during even a single glacial fluctuation. The meaning of cosmic uniformity has been explained in the preceding chapter. Its relation to the other types of climatic sequences seems to be that it sets sharply defined limits beyond which no change of any kind has ever gone since life, as we know it, first began. Secular progression, on the other hand, means that in spite of all manner of variations, now this way and then the other, the normal climate of the Earth, if there is such a thing, has on the whole probably changed a little, perhaps becoming more complex. After each period of continental uplift and glaciation, for such are preeminently the times of complexity, it is doubtful whether the Earth has ever returned to quite its former degree of monotony. Today the Earth has swung away from the great diversity of the glacial period, yet we still have contrasts of what seem to us great magnitude. In low depressions such as Turfan in the central deserts of Eurasia, the thermometer sometimes ranges from 0 degrees Fahrenheit in the morning to 60 degrees in the shade at noon. On a cloudy day in the Amazon forest close to the seashore, on the contrary, the temperature for months may rise to 85 degrees by day and sink no lower than 75 degrees at night. The reasons for the secular progression of the Earth's climate appear to be intimately connected with those which have caused the next, and in many respects, more important types of climatic sequence, which consists of geological oscillations. Both the progression and the oscillations seem to depend largely on three purely terrestrial factors. First, condition of the Earth's interior, including both internal heat and contraction. Second, the salinity and movement of the ocean. And third, the composition and amount of the atmosphere. To begin with the Earth's interior, its loss of heat appears to be an almost negligible factor in explaining either a secular progression or a geological oscillation. According to both the nebular and the planetesimal hypothesis, the Earth's crust appears to be colder now than it was hundreds or thousands of millions of years ago. The emission of eternal heat, however, has probably ceased to be of much climatic significance near the beginning of the geological record. For in southern Canada, glaciation occurred very early in the Proterozoic era. On the other hand, the contraction of the Earth has produced remarkable effects throughout the whole of geological time. It has lessened the Earth's circumference by 1,000 miles or more, as appears from the way in which the rocks have been folded and thrust bodily over one another. According to the laws of dynamics, this must have increased the speed of the Earth's rotation, thus shortening the day, and also having the more important effect of increasing the bulge at the equator. On the other hand, recent investigations indicate that tidal retardation has probably diminished the Earth's rate of rotation more than seemed probable a few years ago, thus lengthening the day and diminishing the bulge at the equator. Thus two opposing forces have been at work, one causing acceleration and one retardation. Their combined effect may have been a factor in causing secular progression of climate. It almost certainly was of much importance in causing pronounced oscillations first one way and then the other. This matter, together with most of those touched in these first chapters, will be explained in later parts of the book. On the whole, the tendency appears to have been to create climatic diversity in place of uniformity. The increasing salinity of the oceans may have been another factor in producing secular progression, although of slight importance in respect to oscillations. While the oceans were still growing in volume, it is generally assumed that they must have been almost fresh for a vast period, although Chamberlain thinks that the change in salinity has been much less than is usually supposed. So far as the early oceans were fresher than those of today, their deep-sea circulation must have been less hampered than now by the heavy saline water which is produced by evaporation in warm regions. Although this saline water is warm, its weight causes it to descend instead of moving poleward in a surface current. This descent slows up the rise of the cold water, which is moved along in the depths of the ocean from high latitudes, and thus checks the general oceanic circulation. If the ancient oceans were fresher and hence had a freer circulation than now, a more rapid interchange of polar and equatorial water presumably tended to equalize the climate of all latitudes. Again, although the Earth's atmosphere has probably changed far less during geological times than was formerly supposed, its composition has doubtless varied. The total volume of nitrogen has probably increased, for that gas is so inert that when it once becomes a part of the air, it is almost sure to stay there. On the other hand, the proportions of oxygen, carbon dioxide, and water vapor must have fluctuated. Oxygen is taken out constantly by animals and by all the processes of rock weathering. But on the other hand, the supply is increased when plants break up new carbon dioxide derived from volcanoes. As for the carbon dioxide, it appears probable that in spite of the increased supply furnished by volcanoes, the great amounts of carbon which have gradually been locked up in coal and limestone have appreciably depleted the atmosphere. Water vapor also may be less abundant now than in the past, for the presence of carbon dioxide raises the temperature a little and thereby enables the air to hold more moisture. When the area of the oceans has diminished, and this has recurred very often, this likewise would tend to reduce the water vapor. Moreover, even a very slight diminution of the amount of heat given off by the earth, or a decrease in evaporation because of higher salinity in the oceans, would tend in the same direction. Now, carbon dioxide and water vapor both have a strong blanketing effect, whereby heat is prevented from leaving the earth. Therefore, the probable reduction in the carbon dioxide of the water vapor of the Earth's atmosphere has apparently tended to reduce the climatic monotony and create diversity and complexity. Hence, in spite of many reversals, the general tendency of changes, not only in the Earth's interior and in the oceans, but also in the atmosphere, appears to be a secular progression from a relatively monotonous climate in which the evolution of higher organic forms would scarcely be rapid to an extremely diverse and complex climate, highly favorable to progressive evolution. The importance of these purely terrestrial agencies must not be lost sight of when we come to discuss other agencies outside the Earth. Table 2. The next type of climatic sequence is geological oscillation. This means slow swings that last millions of years. At one extreme of such an oscillation, the climate all over the world is relatively monotonous. It returns, as it were, toward the primeval conditions at the beginning of the secular progression. At such times, magnolias, sequinas, figs, tree ferns, and many other types of subtropical plants grew far north in places like Greenland, as is well known from their fossil remains of Middle Cenozoic time. For example, at these same times, and also at many others, before such high types of plants had evolved, reef-making corals throve in great abundance in seas which covered what is now Wisconsin, Michigan, Ontario, and other equally cool regions. Today these regions have an average temperature of only about 70 degrees Fahrenheit in the warmest month, and average well below freezing in winter. No reef-making corals can now live where the temperature averages below 68 degrees Fahrenheit. The resemblance of the ancient corals to those of today makes it highly probable that they were equally sensitive to low temperature. Thus, in the mild portions of a geological oscillation, the climate seems to have been so equable and uniform that many plants and animals could live 1,500, and at other times even 4,000 miles farther from the equator than now. At such times the lands in middle and high latitudes were low and small, and the oceans extended widely over the continental platforms. Thus unhampered ocean currents had an opportunity to carry the heat of low latitudes far toward the poles. Under such conditions, especially if the conception of the great sub-equatorial continent of Gondwana land is correct, the trade winds and the westerlies must have been stronger and steadier than now. This would not only enable the westerlies, which are really southwesterlies, to carry more heat than now to high latitudes, but would still further strengthen the ocean currents. At the same time, the air presumably contained an abundance of water vapor derived from the broad oceans, and an abundance of atmospheric carbon dioxide inherited from a preceding time when volcanoes contributed much carbon dioxide to the air. These two constituents of the atmosphere may have exercised a pronounced blanketing effect whereby the heat of the earth with its long wavelengths was kept in, although the energy of the sun with its shorter wavelengths was not markedly kept out. Thus everything may have combined to produce mild conditions in high latitudes, and to diminish the contrast between equator and pole, and between summer and winter. Such conditions perhaps carry in themselves the seeds of decay. At any rate, while the lands lie quiet during a period of mild climate, great strains must accumulate in the crust because of the Earth's contraction and tidal retardation. At the same time, the great abundance of plants upon the low-lying plains with their mild climates, and the marine creatures upon the broad continental platforms, deplete the atmospheric carbon dioxide. Part of this is locked up as coal, and part as limestone derived from marine plants as well as animals. Then something happens so that the strains and stresses of the crust are released. The seafloors sink, the continents become relatively high and large, mountain ranges are formed, and the former plains and emergent portions of the continental platforms are eroded into hills and valleys. The large size of the continents tends to create deserts and other types of climatic diversity. The presence of mountain ranges checks the free flow of winds and also creates diversity. The ocean currents are likewise checked, altered, and diverted so that the flow of heat from low to high latitudes is diminished. At the same time, evaporation from the ocean diminishes so that a decrease in water vapor combines with the previous depletion of carbon dioxide to reduce the blanketing effect of the atmosphere. Thus, upon periods of mild monotony, there supervene periods of complexity, diversity, and severity. Turn to Table 1 and see how a glacial climate again and again succeeds a time when relative mildness prevailed almost everywhere. Or examine Figure 1 and notice how the lines representing temperatures go up and down. In the figure, Shoeshirt makes it clear that when the lands have been large and mountain making has been important, as shown by the high parts of the lower shaded area, the climate has been severe, as shown by the descent of the snow line, the upper shaded area. In the diagram, the climatic oscillations appear short, but this is merely because they have been crowded together, especially in the left-hand or early part. There, an inch in length may represent 100 million years. Even at the right-hand end, an inch is equivalent to several million years. The severe part of the climatic oscillation, as well as the mild part, will be shown in later chapters to bear in itself certain probable seeds of decay. While the lands are being uplifted, volcanic activity is likely to be vigorous and to add carbon dioxide to the air. Later, as the mountains are worn down by the many agencies of water, wind, ice, and chemical decay, although much carbon dioxide is locked up by the carbonation of the rocks, the carbon locked up in the coal is set free and increases the carbon dioxide of the air. At the same time, the continents settle slowly downward, for the Earth's crust, though rigid as steel, is nevertheless slightly viscous, and will flow if subjected to sufficiently great and enduring pressure. The area from which evaporation can take place is thereby increased because of the spread of the oceans over the continents, and water vapor joins with the carbon dioxide to blanket the Earth and thus tends to keep it uniformly warm. Moreover, the diminution of the lands frees the ocean currents from restraints and permits them to flow more freely from low latitudes to high. Thus, in the course of millions of years, there is a return towards monotony. Ultimately, however, new stresses accumulate in the Earth's crust, and the way is prepared for another great oscillation. Perhaps the setting free of the stresses takes place simply because the strain at last becomes irresistible. It is also possible, as we shall see, that an external agency sometimes adds to the strain and thereby determines the time at which a new oscillation shall begin. In Table 2, the types of climatic sequences which follow geologic oscillations are glacial fluctuations, orbital precessions, and historical pulsations. Glacial fluctuations and historical pulsations appear to be the same type, except as to severity and duration, and hence may be considered together. They will be treated briefly here because the theories as to their causes are outlined in the next two chapters. Oddly enough, although the historic pulsations lie much closer to us than do the glacial fluctuations, they were not discovered until 2 or 3 generations later and are still much less known. The most important feature of both sequences is the swing from a glacial to an interglacial epoch, or from the arsis, or accentuated part of an historical pulsation, to the thesis or unaccented part. In a glacial epoch, or in the arsis of an historical pulsation, storms are usually abundant and severe. The mean temperature is lower than usual. Snow accumulates in high latitudes or upon lofty mountains. For example, in the last such period, during the 14th century, great floods and droughts occurred alternately around the North Sea. It was several times possible to cross the Baltic Sea from Germany to Sweden on the ice, and the ice of Greenland advanced so much that shore ice caused the Norsemen to change their sailing route between Iceland and the Norse colonies in southern Greenland. At the same time, in low latitudes and in parts of the continental interior, there is a tendency toward diminished rainfall and even toward aridity and the formation of deserts. In Yucatan, for example, a diminution in tropical rainfall in the 14th century seems to have given the Mayas a last opportunity for a revival of their decaying civilization. Figure 1 is displayed on the previous page. Climatic changes and mountain building, after Schuchert in The Evolution of the Earth and its Inhabitants, edited by R.S. Lull. Diagram showing the time and perhaps probable extent of the more or less marked climatic changes in the geological history of North America and of its elevation into chains of mountains. Among the climatic sequences, glacial fluctuations are perhaps of the most vital import from the standpoint of organic evolution. From the standpoint of human history, the same is true of climatic pulsations. Glacial epochs have repeatedly wiped out thousands upon thousands of species and played a part in the origin of entirely new types of plants and animals. This is best seen when the life of the Pennsylvanian is contrasted with that of the Permian. An historic pulsation may wipe out an entire civilization and permit a new one to grow up with a radically different character. Hence it is not strange that the causes of such climatic phenomena have been discussed with extraordinary vigor. In few realms of science has there been a more imposing and more interesting array of theories. In this book we shall consider the more important of these theories. A new solar or cyclonic hypothesis and the hypothesis of change in the form of altitude of the land will receive the most attention. But the other chief hypotheses are outlined in the next chapter and are frequently referred to throughout the volume. Between glacial fluctuations and historical pulsations in duration, but probably less severe than either, come orbital precisions. These stand in a group by themselves and are more akin to seasonal alternations than to any other type of climatic sequence. They must have occurred with absolute regularity ever since the Earth began to revolve around the Sun in its present elliptical orbit. Since the orbit is elliptical, and since the Sun is in one of the two foci of the eclipse, the Earth's distance from the Sun varies. At present the Earth is nearest the Sun in the northern winter, hence the rigour of winter in the northern hemisphere is mitigated, while that of the southern hemisphere is increased. In about 10,000 years this condition will be reversed, and another 10,000 the present conditions will return once more. Such climatic precessions, as we may here call them, must have occurred unnumbered times in the past, but they do not appear to have been large enough to leave in the fossils of the rocks any traces that can be distinguished from those of other climatic sequences. We come now to Bruckner periods and sunspot cycles. The Bruckner periods have a length of about 33 years. Their existence was suggested at least as long ago as the days of Sir Francis Bacon, whose statement about them is quoted on the flyleaf of this book. They have since been detected by a careful study of the records of the time of harvest, vintage, and opening of rivers to navigation, and the rise or fall of lakes like the Caspian Sea. In his book on Klimaschwankungen, Seat 1700, Bruckner has collected an uncommonly interesting assortment of facts as to the climate of Europe for more than 2 centuries. More recently, by a study of the rate of growth of trees, Douglas, in his book on climatic cycles and tree growth, has carried the subject still further. In general, the nature of the 33-year periods seems to be identical with that of the 11 or 12-year sunspot cycle, on the one hand, and of historic pulsations on the other. For a century, observers have noted that the variations in the weather, which everyone notices from year to year, seem to have some relation to sunspots. For generations, however, the relationship was discussed without leading to any definite conclusion. The trouble was that the same change was supposed to take place in all parts of the world. Hence, when every sort of change was found somewhere at any given sunspot stage, it seemed as though there could not be a relationship. Of late years, however, the matter has become fairly clear. The chief conclusions are, first, that when sunspots are numerous, the average temperature of the Earth's surface is lower than normal. This does not mean that all parts are cooler, for while certain large areas grow cool, others of less extent become warm at times of many sunspots. Second, at times of many sunspots, storms are more abundant than usual, but are also confined somewhat closely to certain limited tracts, so that elsewhere a diminution of storminess may be noted. This whole question is discussed so fully in Earth and Sun that it need not detain us further in this preliminary view of the whole problem of climate. Suffice it is to say that a study of the sunspot cycle leads to the conclusion that it furnishes a clue to many of the unsolved problems of the climate of the past, as well as a key to prediction of the future. Passing by the seasonal alternations, which are fully explained as a result of the revolution of the Earth around the Sun, we may merely point out that, like the daily vibrations which bring Table 2 to a close, they emphasize the outstanding fact that the main control of terrestrial climate is the amount of energy received from the Sun. This same principle is illustrated by Pleionian migrations. The term pleioin comes from a Greek word meaning more. It was taken by Arctowski to designate areas or periods where there is an excess of some climatic element, such as atmospheric pressure, rainfall, or temperature. Even if the effect of the seasons is eliminated, it appears that the course of these various elements does not run smoothly. As everyone knows, a period like the autumn of 1920 in the eastern United States may be unusually warm, while the succeeding period may be unseasonably cool. These departures from the normal show a certain rough periodicity. For example, there is evidence of a period of about 27 days corresponding to the Sun's rotation and formerly supposed to be due to the Moon's revolution, which occupies almost the same length of time. Still, other periods appear to have average duration of about 3 months and of between 2 and 3 years. 2 remarkable discoveries have recently been made in respect to such pleioins. One is that a given type of change usually occurs simultaneously in a number of well-defined but widely separated centers, while a change of an opposite character arises in another equally well-defined but quite different set of centers. In general, areas of high pressure have one type of change and areas of low pressure the other type. So systematic are these relationships, and so completely do they harmonize in widely separated parts of the Earth, that it seems certain that they must be due to some outside cause, which in all probability can be only the Sun. The second discovery is that pleioins, when once formed, travel irregularly along the Earth's surface. Their paths have not yet been worked out in detail, but a general migration seems well established. Because of this, it is probable that if unusually warm weather prevails in one part of a continent at a given time, the thermopleon, or excessive heat, will not vanish but will gradually move away in some particular direction. If we knew the path that it would follow, we might predict the general temperature along its course for some months in advance. The paths are often irregular, and the pleons frequently show a tendency to break up or suddenly revive. Probably this tendency is due to variations in the Sun. When the Sun is highly variable, the pleons are numerous and strong, and extremes of weather are frequent. Taken as a whole, the pleons offer one of the most interesting and hopeful fields, not only for the student of the causes of climatic variations, but for the man who is interested in the practical question of long-range weather forecasts. Like many other climatic phenomena, they seem to represent the combined effect of conditions in the Sun and upon the Earth itself. The last of the climatic sequences which require explanation is the cyclonic vacillations. These are familiar to everyone, for they are the changes of weather which occur at intervals of a few days or a week or two at all seasons in large parts of the United States, Europe, Japan, and some of the other progressive parts of the Earth. They do not, however, occur with great frequency in equatorial regions, deserts, and many other regions. Up to the end of the last century, it was generally supposed that cyclonic storms were purely terrestrial in origin. Without any adequate investigation, it was assumed that all irregularities in the planetary circulation of the winds arise from an irregular distribution of heat due to conditions within or upon the Earth itself. These irregularities were supposed to produce cyclonic storms in certain limited belts, but not in most parts of the world. Today this view has been rapidly modified. Undoubtedly, the irregularities due to purely terrestrial conditions are one of the chief contributory causes of storms, but it begins to appear that solar variations also play a part. It has been found, for example, that not only the mean temperature of the Earth's surface varies in harmony with the sunspot cycle, but that the frequency and severity of storms vary in the same way. Moreover, it has been demonstrated that the sun's radiation is not constant, but is subject to innumerable variations. This does not mean that the sun's general temperature varies, but merely that at some times heated gases are ejaculated rapidly to high levels so that a sudden wave of energy strikes the Earth. Thus the present tendency is to believe that the cyclonic variations, the changes of weather which come and go in such a haphazard, irresponsible way, are partially due to causes pertaining to the Earth itself and partially to the Sun. From this rapid survey of the types of climatic sequence, it is evident that they may be divided into four great groups. First comes cosmic uniformity, one of the most marvelous and incomprehensible of all known facts. We simply have no explanation which is in any respect adequate. Next comes secular progression and geologic oscillations, two types of changes which seem to be due mainly to purely terrestrial causes, that is, to changes in the lands, the oceans, and the air. The general tendency of these changes is toward complexity and diversity, thus producing progression, but they are subject to frequent reversals which give rise to oscillations lasting millions of years. The processes by which the oscillations take place are fully discussed in this book. Nevertheless, because they are fairly well understood, they are deferred until after the third group of sequences has been discussed. This group includes glacial fluctuations, historic pulsations, Bruckner periods, sunspot cycles, Pleionian migrations, and cyclonic vacillations. The outstanding fact in regard to all of these is that while they are greatly modified by purely terrestrial conditions, they seem to owe their origin to variations in the Sun. They form the chief subject of Earth and Sun, and in their larger phrases are the most important topic of this book also. The last group of sequences includes orbital precessions, seasonal alternations, and daily variations. These may be regarded as purely solar in origin, yet their influence, like that of each of the other groups, is much modified by the Earth's own conditions. Our main problem is to separate and explain the two great elements in climatic changes, the effects of the Sun on the one hand, and of the Earth on the other. End of Section 2. Section 3 of Climatic Changes, Their Nature and Causes by Ellsworth Huntington. This LibriVox recording is in the public domain. Recorded by Leon Harvey. Chapter 3. Hypothesis of Climatic Change. The next step in our study of climate is to review the main hypothesis as to the causes of glaciation. These hypotheses apply also to other types of climatic changes. We shall concentrate on glacial periods, however, not only because they are the most dramatic and well-known types of change, but because they have been more discussed than any other and have also had great influence on evolution. Moreover, they stand near the middle of the types of climatic sequences, and an understanding of them does much to explain the others. In reviewing the various theories, we shall not attempt to cover all the ground, but shall merely state the main ideas of the few theories which have had an important influence upon scientific thought. The conditions which any satisfactory climatic hypothesis must satisfy are briefly as follows. 1. Due weight must be given to the fact that changes of climate are almost certainly due to the combined effect of a variety of causes, both terrestrial and solar or cosmic. 2. Attention must also be paid to both sides in the long controversy as to whether glaciation is due primarily to a diminution in the Earth's supply of heat or to a redistribution of the heat through changes in atmospheric and oceanic circulation. At present, the great majority of authorities are on the side of a diminution of heat, but the other view also deserves study. 3. A satisfactory hypothesis must explain the frequent synchronism between two great types of phenomena. First, movements of the Earth's crust whereby continents are uplifted and mountains upheaved, and second, great changes of climate which are usually marked by relatively rapid oscillations from one extreme to another. 4. No hypothesis can find acceptance unless it satisfies the somewhat exacting requirements of the geological record, with its frequent but irregular repetition of long, mild periods, relatively cool or intermediate periods like the present, and glacial periods of more or less severity, and perhaps accompanying the more or less widespread uplifting of continents. At least during the later glacial periods, the hypothesis must explain numerous climatic epochs and stages superposed upon a single general period of continental upheaval. Moreover, although historical geology demands cycles of varied duration and magnitude, it has not furnished evidence of any rigid periodicity causing the cycles to be uniform in length or intensity. 5. Most important of all, a satisfactory explanation of climatic changes and crustal deformation must take account of all the agencies which are now causing similar phenomena. Whether any other agencies should be considered is open to question, although the relative importance of existing agencies may have varied. 1. Kroll's eccentricity theory. One of the most ingenious and most carefully elaborated scientific hypotheses is Kroll's precessional hypothesis as to the effect of the Earth's own motions. So well was this worked out that it was widely accepted for a time and still finds a place in popular but unscientific books, such as Wells' Outline of History, and even in scientific works like Wright's Quaternary Ice Age. The gist of the hypothesis has already been given in connection with the type of climatic sequence known as orbital precessions. The Earth is 93 million miles away from the Sun in January and 97 million in July. The Earth's axis precesses, however, just as does that of a spinning top. Hence arises what is known as the precession of the equinoxes, that is, a steady change in the season at which the Earth is in perihelion, or nearest to the Sun. In the course of 21,000 years, the time of perihelion varies from early in January through the entire 12 months and back to January. Moreover, the Earth's orbit is slightly more elliptical at certain periods than at others, for the planets sometimes become bunched so that they all pull the Earth in one direction. Hence, once in about 100,000 years, the effect of the elliptical shape of the Earth's orbit is at a maximum. Kroll argued that these astronomical changes must alter the Earth's climate, especially by their effect on winds and ocean currents. His elaborate argument contains a vast amount of valuable material. Later investigation, however, seems to have proven the inadequacy of this hypothesis. In the first place, the supposed cause does not seem nearly sufficient to produce the observed results. Second, Kroll's hypothesis demands that glaciation in the northern and southern hemisphere take place alternately. A constantly growing collection of facts, however, indicates that glaciation does not occur in the two hemispheres alternately, but at the same time. Third, the hypothesis calls for the constant and frequent repetition of glaciation at absolutely regular intervals. The geological record shows no such regularity, for sometimes several glacial epochs follow in relatively close succession at irregular intervals of perhaps 50 to 200,000 years, and thus from a glacial period, and then for millions of years there are none. Fourth, the eccentricity hypothesis provides no adequate explanation for the glacial stages or sub-epochs, the historical pulsations, and other smaller climatic variations, which are superposed upon glacial epochs and upon one another in bewildering confusion. In spite of these objections, there can be little question about the eccentricity of the Earth's orbit and the precession of the equinoxes, with the resulting change in the season of perihelion, must have some climatic effect. Hence Kroll's theory deserves a permanent, though minor place in any full discussion of the causes of climatic changes. 2. The carbon dioxide theory. At about the time that the eccentricity theory was being relegated to a minor niche, a new theory was being developed which soon exerted a profound influence upon geological thought. Chamberlain, adopting an idea suggested by Tyndall, fired the imagination of geologists by his skillful exposition of the part played by carbon dioxide in causing climatic changes. Today this theory is probably more widely accepted than any other. We have already seen that the amount of carbon dioxide gas in the atmosphere has a decided climatic importance. Moreover, there can be little doubt that the amount of that gas in the atmosphere varies from age to age in response to the extent to which it is set free by volcanoes, consumed by plants, combined with rocks in the process of weathering, dissolved in the ocean, or locked up in the form of coal and limestone. The main question is whether such variations can produce changes so rapid as glacial epochs and historical pulsations. Abundant evidence seems to show that the degree to which the air can be warmed by carbon dioxide is sharply limited. Humphreys, in his excellent book on the physics of the air, calculates that a layer of carbon dioxide 40 centimeters thick has practically as much blanketing effect as a layer indefinitely thicker. In other words, 40 centimeters of carbon dioxide, while having no appreciable effect on sunlight coming toward the Earth, would filter out and thus retain in the atmosphere all the outgoing terrestrial heat that carbon dioxide is capable of absorbing. Adding more would be like adding another filter when the one in operation is already done all that particular kind of filter is capable of doing. According to Humphrey's calculations, a doubling of the carbon dioxide in the air would, in itself, raise the average temperature about 1.3 degrees Celsius, and further carbon dioxide would have practically no effect. Reducing the present supply by half would reduce the temperature by essentially the same amount. The effect must be greater, however, than would appear from the figures given above, for any change in temperature has an effect on the amount of water vapor, which in turn causes further changes of temperature. Moreover, as Chamberlain points out, it is not clear whether Humphreys allows for the fact that when the 40 centimeters of CO2 nearest the Earth has been heated by terrestrial radiation, it in turn radiates half its heat outward and half inward. The outward half is all absorbed in the next layer of carbon dioxide and so on. The process is much more complex than this, but the end result is that even the last increment of CO2, that is, the outermost portions in the upper atmosphere, must apparently absorb an infinitesimally small amount of heat. This, in fact, plus the effect of water vapor, would seem to indicate that a doubling or halving of the amount of CO2 would have an effect of more than 1.3 degrees Celsius. A change of even 2 degrees Celsius above or below the present level of the Earth's mean temperature would be of very appreciable climatic significance, for it is commonly believed that during the height of the glacial period, the mean temperature was only 5 to 8 degrees Celsius lower than now. Nevertheless, variations in atmospheric carbon dioxide do not necessarily seem competent to produce the relatively rapid climatic fluctuations of glacial epochs and historical pulsations, as distinguished from the longer swing of glacial periods and geological eras. In Chamberlain's view, as in ours, the elevation of the land, the moderation of the currents of the air and of the ocean, and all that goes with elevation as a topographic agency constitute a primary cause of climatic changes. A special effect of this is the removal of carbon dioxide from the air by the enhanced process of weathering. This, as he carefully states, is a very slow process, and cannot of itself lead to anything so sudden as the oncoming of glaciation. But here comes Chamberlain's most distinctive contribution to the subject, namely the hypothesis that changes in atmospheric temperature arising from variations in atmospheric carbon dioxide are able to cause a reversal of the deep-sea oceanic circulation. According to Chamberlain's view, the ordinary oceanic circulation of the greater part of geological time was the reverse of the present circulation. Warm water descended to the ocean depths in low latitudes, kept its heat while creeping slowly poleward, and rose in high latitudes, producing the warm climate which enabled corals, for example, to grow in high latitudes. Chamberlain holds this opinion largely because there seems to him to be no other reasonable way to account for the enormously long warm periods when heat-loving forms of life lived in what are now polar regions of ice and snow. He explains this reverse circulation by supposing that an abundance of atmospheric carbon dioxide, together with a broad distribution of the oceans, made the atmosphere so warm that the evaporation in low latitudes was far more rapid than now. Hence the surface water of the ocean became a relatively concentrated brine. Such a brine is heavy and tends to sink, thereby setting up an oceanic circulation the reverse of that which now prevails. At present the polar waters sink because they are cold, and hence contract. Moreover, when they freeze, a certain amount of salt leaves the ice and thereby increases the salinity of the surrounding water. Thus the polar water sinks to the depths of the ocean. Its place is taken by warmer and lighter water from low latitudes, which moves poleward along the surface, and at the same time the cold water of the ocean depths is forced equatorward below the surface. But if the equatorial waters were so concentrated that a steady supply of highly saline water kept descending to low levels, the direction of the circulation would have to be reversed. The time when this would occur would depend upon the delicate balance between the downward tendencies of the cold polar water and of the warm saline equatorial water. Suppose that while such a reverse circulation prevailed, the atmospheric CO2 should be depleted, and the air cooled so much that the concentration of the equatorial waters by evaporation was no longer sufficient to cause them to sink. A reversal would take place. The present type of circulation would be inaugurated, and the whole earth would suffer a chill because the surface of the ocean would become cool. The cool surface water would absorb carbon dioxide faster than the previous warm water had done, for heat drives off gases from water. This would hasten the cooling of the atmosphere still more, not only directly but by diminishing the supply of atmospheric moisture. The result would be glaciation. But ultimately the cold waters of the higher latitudes would absorb all the carbon dioxide they could hold. The slow equatorial creep would at length permit the cold water to rise to the surface in low latitudes. There the warmth of the equatorial sun and the depleted supply of carbon dioxide in the air would combine to cause the water to give up its carbon dioxide once more. If the atmosphere had been sufficiently depleted by that time, the rising waters in low latitudes might give up more carbon dioxide than the cold polar waters absorbed. Thus the atmospheric supply would increase, the air would again grow warm, and a tendency towards glaciation or toward an interglacial condition would arise. At such times the oceanic circulation is not supposed to have been reversed, but merely to have been checked and made slower by the increasing warmth. Thus interglacial conditions like those of today, or even considerably warmer, are supposed to have been produced with the present type of circulation. The emission of carbon dioxide in low latitudes could not permanently exceed the absorption in high latitudes. After the present type of circulation was finally established, which might take tens of thousands of years, the two would gradually become equal. Then the conditions which originally caused the oceanic circulation to be reversed would again destroy the balance. The atmospheric carbon dioxide would be depleted, the air would grow cooler, and the type of glaciation would be repeated. Each cycle would be shorter than the last, for not only would the swings diminish like those of a pendulum, but the agencies that were causing the main depletion of the atmospheric carbon dioxide would diminish in intensity. Finally, as the lands became lower through erosion and submergence, and as the processes of weathering became correspondingly slow, the air would gradually be able to accumulate carbon dioxide. The temperature would increase, and at length the oceanic circulation would be reversed again. When the warm saline waters of low latitudes finally began to sink and to set up a flow of warm water poleward in the depths of the ocean, a glacial period would definitely come to an end. This hypothesis has been so skillfully elaborated and contains so many important elements that one can scarcely study it without profound admiration. We believe that it is of the utmost value as a step toward the truth, and especially because it emphasizes the great function of oceanic circulation. Nevertheless, we are unable to accept it in full for several reasons, which may here be stated very briefly. Most of them will be discussed fully in later pages. 1. While a reversal of the deep sea circulation would undoubtedly be of great climatic importance and would produce a warm climate in high latitudes, we see no direct evidence of such a reversal. It is equally true that there is no conclusive evidence against it, and the possibility of a reversal must not be overlooked. There seem, however, to be other modifications of atmospheric and oceanic circulation which are unable to produce the observed results. 2. There is much, and we believe conclusive evidence, that a mere lowering of temperature would not produce glaciation. What seems to be needed is changes in atmospheric circulation and precipitation. The carbon dioxide hypothesis has not been nearly so fully developed on the meteorological side as in other respects. 3. The carbon dioxide hypothesis seems to demand that the oceans should have been almost as saline as now in the Proterozoic era at the time of the first known glaciation. Chamberlain holds that such was the case, but the constant supply of saline material brought to the ocean by rivers and the relatively small deposition of such material on the seafloor seems to indicate that the early oceans must have been much fresher than those of today. 4. The carbon dioxide hypothesis does not attempt to explain minor climatic fluctuations such as post-glacial stages and historic pulsations, but these appear to be of the same nature as glacial epochs, differing only in degree. 5. Another reason for hesitation in accepting the carbon dioxide hypothesis as a full explanation of glacial fluctuations is a highly complex and non-observable character of the explanation of the alternation of glacial and interglacial epochs and of their constantly decreasing length. 6. Most important of all, a study of the variations of weather and of climate as they are disclosed by present records and by historic past suggests that there are now in action certain other causes which are competent to explain glaciation without recourse to a process whose action is beyond the realm of observation. These considerations lead to the conclusion that the carbon dioxide hypothesis and the reversal of the oceanic circulation should be regarded as a tentative rather than a final explanation of glaciation. Nevertheless, the action of carbon dioxide seems to be an important factor in producing the longer oscillations of climate from one geological era to another. It probably plays a considerable part in preparing the way for glacial periods and in making it possible for other factors to produce the more rapid changes which have so deeply influenced organic evolution. 3. The form of the land. Another great cause of climatic change consists of a group of connected phenomena dependent upon movements of the Earth's crust. As to the climatic potency of changes in the lands, there is practical agreement among students of climatology and glaciation that the height and extent of the continents, the location, size, and orientation of mountain ranges, and the opening and closing of oceanic gateways at places like Panama, and the consequent diversion of oceanic currents exert a profound effect upon climate, can scarcely be questioned. Such changes may be introduced rapidly, but their disappearance is usually slow compared to the rapid pulsations to which climate has been subject during historic times and during stages of glacial retreat and advance, or even in comparison with the epochs into which the Pleistocene, Permian, and perhaps earlier glacial periods have been divided. Hence, while crustal movements appear to be more important than the eccentricity of the Earth's orbit or the amount of carbon dioxide in the air, they do not satisfactorily explain glacial fluctuations, historic pulsations, and especially the present little cycles of climatic change. All these changes involve a relatively rapid swing from one extreme to another, while an upheaval of a continent, which is at best a slow geologic process, apparently cannot be undone for a long, long time. Hence such an upheaval, if acting alone, would lead to a relatively long-lived climate of a somewhat extreme type. It would help to explain the long swings, or geologic oscillations between a mild and uniform climate at one extreme and a complex and varied climate at the other. But it would not explain the rapid climatic pulsations which are closely associated with great movements of the Earth's crust. It might prepare the way for them, but could not cause them. That this conclusion is true is borne out by the fact that vast mountain ranges, like those at the close of the Jurassic and Cretaceous, are upheaved without bringing on glacial climates. Moreover, the marked Permian Ice Age follows long after the birth of the Hercynian Mountains and before the rise of others of later Permian origin. 4. The volcanic hypothesis. In the search for some cause of climatic change, which is highly efficient and yet able to vary rapidly and independently, Abbott, Fowle, Humphreys, and others have concluded that volcanic eruptions are the missing agency. In Physics of the Air, Humphreys gives a careful study of the effect of volcanic dust upon terrestrial temperature. He begins with a mathematical investigation of the size of dust particles and their quantity after certain eruptions. He demonstrates that the power of such particles to deflect light of short wavelengths coming from the sun is perhaps 30 times more than that power to retain the heat radiated in long waves from the Earth. Hence it is estimated that if a Krakatoa were to belch forth dust every year or two, the dust veil might cause a reduction of about 6 degrees Celsius in the Earth's surface temperature. As in every such complicated problem, some of the author's assumptions are open to question, but this touches their quantitative and not their qualitative value. It seems certain that if volcanic explosions were frequent enough and violent enough, the temperature of the Earth's surface would be considerably lowered. Actual observation supports this theoretical conclusion. Humphreys gathers together and amplifies all that he and Abbott and Fowle have previously said as to observations of the sun's thermal radiation by means of the pyrheliometer. This summing up of the relations between the heat received from the sun and the occurrence of explosive volcanic eruptions leaves little room for doubt that at frequent intervals during the last century and a half a slight lowering of terrestrial temperature has actually occurred after great eruptions. Nevertheless, it does not justify Humphreys' final conclusion that phenomena within the Earth itself suffice to modify its own climate. That these and these alone have actually caused great changes time and again in their geologic past. Humphreys sees so clearly the importance of the purely terrestrial point of view that he unconsciously slights the cosmic standpoint and ignores the important solar facts which he himself adduces elsewhere at considerable length. In addition to this, the degree to which the temperature of the Earth as a whole is influenced by volcanic eruptions is by no means so clear as is the fact that there is some influence. Arctowski, for example, has prepared numerous curves showing the march of temperature month after month for many years. During the period from 1909 to 1913, which includes the great eruption of Katmai in Alaska, low temperature is found to have prevailed at the time of the eruption. But, as Arctowski puts it, on the basis of the curves for 150 stations in all parts of the world, the supposition that these abnormally low temperatures were due to the veil of volcanic dust produced by the Katmai eruption of June 6, 1912, is completely out of the question. If that had been the case, the temperature would have decreased from that date on, whereas it was decreasing for more than a year before that date. Köppen, in his comprehensive study of temperature for 100 years, also presents a strong argument against the idea that volcanic eruptions have an important place in determining the present temperature of the Earth. A volcanic eruption is a sudden occurrence. Whatever effect is produced by dust thrown into the air must occur within a few months, or as soon as the dust has had an opportunity to be wafted to the region in question. When the dust arrives, there will be a rapid drop through the few degrees of temperature which the dust is supposed to be able to account for, and thereafter a slow rise of temperature. If volcanic eruptions actually cause a frequent lowering of terrestrial temperature in the 100 years studied by Köppen, there should be more cases where the annual temperature is decidedly below the normal than where it shows a large departure in the opposite direction. The contrary is actually the case. A still more important argument is the fact that the Earth is now in an intermediate condition of climate. Throughout most of geologic time, as we shall see again and again, the climate of the Earth has been milder than now. Regions like Greenland have not been the seat of glaciers, but have been the home of types of plants which now thrive in relatively low latitudes. In other words, the Earth is today only part way from a glacial epoch to what may be called the normal, mild climate of the Earth, a climate in which the contrast from zone to zone was much less than now, and the lower air averaged warmer. Hence it seems impossible to avoid the conclusion that the cause of glaciation is still operating with considerable, although diminished efficiency. But volcanic dust is obviously not operating to any appreciable extent at present, for the upper air is almost free from dust a large part of the time. Again, as Chamberlain suggests, let it be supposed that a Krakatoan eruption every 2 years would produce a glacial period. Unless the most experienced field workers on the glacial formations are quite in error, the various glacial epochs of the Pleistocene glacial period had a joint duration of at least 150,000 years, and perhaps twice as much. That would require 75,000 Krakatoan eruptions. But where are the pits and cones of such eruptions? There has not been time to erode them away since the Pleistocene glaciation. Their beds of volcanic ash would presumably be as voluminous as the glacial beds, but there did not seem to be accumulations of any such size. Even though the same volcanoes suffered repeated explosions, it seems impossible to find sufficient fresh volcanic debris. Moreover, the volcanic hypothesis has not yet offered any mechanism for systematic glacial variations. Hence, while the hypothesis is important, we must search further for the full explanation of glacial fluctuations, historic pulsations, and the Earth's present quasi-glacial climate. 5. The hypothesis of polar wandering. Another hypothesis, which has some adherents, especially among geologists, holds that the position of the Earth's axis has shifted repeatedly during geological times, thus causing glaciation in regions which are not now polar. Astrophysicists, however, are quite sure that no agency could radically change the relation between the Earth and its axis without likewise altering the orbits of the planets to a degree that would be easily recognized. Moreover, the distribution of the centers of glaciation, both the Permian and Pleistocene periods, does not seem to conform to this hypothesis. 6. The thermal solar hypothesis. The only other explanations of the climatic changes of glacial and historic times which now seem to have much standing are two distinct and almost antagonistic solar hypotheses. One is the idea that changes in the Earth's climate are due to variations in the heat emitted by the Sun, and hence in the temperature of the Earth. The other is the entirely different idea that climatic changes arise from solar conditions which cause a redistribution of the Earth's atmospheric pressure, and hence produce changes in winds, ocean currents, and especially storms. This second or cyclonic hypothesis is the subject of a book entitled Earth and Sun, which is to be published as a companion to the present volume. It will be outlined in the next chapter. The other, or thermal hypothesis, may be dismissed briefly. Unquestionably, a permanent change in the amount of heat emitted by the Sun would permanently alter the Earth's climate. There is absolutely no evidence, however, of any such change during geologic time. The evidence as to the Earth's cosmic uniformity and as to secular progression is all against it. Suppose that for 30 or 40,000 years the sun cooled off enough so that the Earth was as cool as during a glacial epoch. As glaciation is soon suggested by a mild climate, some agency would then be needed to raise the sun's temperature. The impact of a shower of meteorites might accomplish this, but that would mean a very sudden heating, such as there is no evidence of in geological history. In fact, there is far more evidence of sudden cooling than of sudden heating. Moreover, it is far beyond the bounds of probability that such an impact should be repeated again and again with just such force as to bring the climate back almost to where it started, and yet to allow for the slight changes which cause solar progression. Another and equally cogent objection to the thermal form of solar hypothesis is stated by Humphreys as follows. A change of the solar constant obviously alters all surface temperatures by a roughly constant percentage. Hence a decrease of the heat from the sun would in general cause a decrease of the interzonal temperature gradients, and this in turn a less vigorous atmospheric circulation, and a less copious rain or snowfall. Exactly the reverse of the condition, namely abundant precipitation, most favourable to extensive glaciation. This brings us to the end of the main hypothesis as to climatic changes. Aside from the solar cyclonic hypothesis, which will be discussed in the next chapter, it appears that variations in the position of the Earth at perihelion have a real, though slight, influence in causing cycles with a length of about 21,000 years. Changes in the carbon dioxide of the air probably have a more important but extremely slow influence upon geologic oscillations. Variations in the size, shape, and height of the continents are constantly causing all manner of climatic complications, but do not cause rapid fluctuations and pulsations. The eruption of volcanic dust appears occasionally to lower the temperature, but its potency to explain the complex climatic changes recorded in the rocks has probably been exaggerated. Finally, although minor changes in the amount of heat given out by the sun occur constantly and have been demonstrated to have a climatic effect, there is no evidence that such changes are the main cause of the climatic phenomena which we are trying to explain. Nevertheless, in connection with the solar changes, they may be of high importance. End of section 3.